Chapter 6 is about composition of substances and solutions. If you have put your calculators away, go ahead and get them back out because we're going to be using them extensively in Chapters 6 and 7. In Chapter 2, we talked about molar mass. Now I'd like to describe a few related concepts. For covalent molecules, we can use either the term molecular mass or formula mass. And these both would describe the mass of a single molecule, and the units on that would be atomic mass units, or AMU. Molecular mass specifically refers to molecules, and formula mass would be the mass based on the chemical formula. For ionic compounds, there are no individual molecules, so the term molecular mass would be inappropriate. Instead, we must use the term formula mass, which would be based on the chemical formula of the ionic compound. If we want to use a larger scale, we can use the term molar mass, and the units on that would be grams per mole. Whether we use the term molecular mass, formula mass, or molar mass, we go about our calculations the same way. We take each of the elements' masses from the periodic table and add them up. So for CHCl3, we would have 1 times the mass of carbon plus 1 times the mass of hydrogen plus 3 times the mass of chlorine from the periodic table and add them up. So for an example of finding the molecular mass, we can find it for aspirin, which is C9H8O4. So all we have to do is take 9 times the mass of carbon plus 8 times the mass of hydrogen plus 4 times the mass of oxygen from the periodic table and add them up. As you do these types of problems, use the full mass on the periodic table that's in front of you, whether it be the periodic table provided on your exam or the periodic table provided by WebAssign as you're doing your homework problems. We can also find a mass of an ionic compound, such as aluminum sulfate. Aluminum sulfate has the formula Al2SO4 in parentheses 3. So this formula tells us that there are 2 aluminums for every 3 sulfate ions. One formula unit of aluminum sulfate would contain 2 aluminums and 3 sulfates. But remember that ionic compounds are a 3-dimensional array of ions, and so there would be many more of each of them. We still go about the calculation the same way. But remember, when we have parentheses, the subscript on the outside of the parentheses gets multiplied by the subscripts on the inside of the parentheses to tell you how many of each type of atom you have. So for aluminum sulfate, we would have 2 aluminums, 3 sulfurs, and 12 oxygens. So to calculate its formula mass, we would take all of those masses from the periodic table and add them up. Now your figure from your textbook said molecular mass, but again, that would be inappropriate for an ionic compound. So it really should say formula mass. We're going to use molecular mass and molar mass in order to do some further calculations in this section. First, we're going to find percent composition based on a chemical formula. Then we'll find an empirical formula based on some experimentally determined masses of some different elements. Our third type of calculation will be finding an empirical formula if we know the percent composition of the elements that make up the compound. And then after doing either 2 or 3, we can do number 4, which is finding molecular formula based on an empirical formula. Percent composition, which will be our first type of calculation, is defined as the percent by mass of a particular element within a compound. Essentially what we're trying to find is how much of a particular compound is made up of a particular element in terms of the masses. The percent composition will be different if the ratios are different. So let's look at 2 similar compounds, potassium chromate and potassium dichromate. Both of these compounds have 2 potassiums in their chemical formula, but the percentage of potassium chromate that is made up of potassium is 40.3%, whereas in potassium dichromate, the potassium only makes up 26.5% of its mass. The reason is that dichromate is a larger ion, and so the 2 potassiums that are with it make up a smaller percentage of the overall mass. Whereas with potassium chromate, the chromate is a smaller ion, and so the potassium makes up a larger percentage overall of the mass of the compound. So the number of potassium atoms did not change, but the percent composition did change because the ratios changed. So how do we calculate percent composition? We take the mass due to one type of element, divide by the mass of all of the elements in the compound, and then we multiply by 100%. Essentially, we're taking the mass of the part divided by the mass of the whole, and then times 100. Another way to think about it is we're going to take the subscript of a particular element and multiply it by the atomic mass of that element from the periodic table. And we divide by the formula mass of the compound, that is the mass of the whole thing, and then times 100. So for potassium chromate, we would need to find its formula mass or molar mass to put on the bottom of the calculation. And so we would have 2 potassiums, 1 chromium, and 4 oxygens. We add up all of those masses and get 194.188. So then that part goes on the bottom of our calculation as our formula mass or molar mass of the compound. And then we just want on top the part that's due to the potassium. So the part that's due to the potassium is 2 times the mass of potassium. So we have 2 times 39.098 divided by our 184.188 times 100 to change to a percentage, and we get the 40.268%. We could do the same type of calculation to find the percent of chromium in potassium chromate, or the percent of oxygen in potassium chromate. We would have something different on the top, but that 194.188 would be the same on the bottom anytime that we have potassium chromate. Here's a question for you. What's the percent composition of hydrogen in C2H2? The correct answer is B, 7.743%. Notice that we're not talking about numbers of atoms. By number of atoms, the hydrogen makes up 50% of the chemical formula, but by mass, which is what we're typically talking about with percent composition, the hydrogen makes up only 7.743%. And that is because hydrogen is lighter than carbon. Our second type of calculation is finding an empirical formula based on some masses that have been experimentally determined. So first we would get the masses of each of the elements in a compound. And we could take those masses in grams and convert them into moles using the molar mass. We learned how to do this in Chapter 2. We take our grams, divide by the molar mass, and that gives us number of moles. Once we have our moles, our second step is writing a preliminary empirical formula based on those numbers of moles. But they will probably not be in whole number form. You will likely have decimal numbers at this point. In order to get them into a whole number form, which is what we like for our chemical formulas, we're going to divide each of our numbers of moles by whichever number of moles is the smallest. And then, if necessary, we'll do a little bit of rounding to get a whole number ratio. So here's an example calculating an empirical formula based on some masses. We found in the lab that we had 1.71 grams of carbon and 0.287 grams of hydrogen, and we want to use that to find the empirical formula. So first we're going to take our grams and convert them into moles. So we'll take our 1.71 grams of carbon, divide by the molar mass of carbon to get moles of carbon. Then we take our 0.287 grams of hydrogen, divide by the molar mass of hydrogen, which is 1.008, and we come out with 0.284 moles of hydrogen. So that tells us the relationship between number of moles of carbon and moles of hydrogen. We can write this as a preliminary empirical formula. We could write it as C with a subscript of 0.142, H with a subscript of 0.284. And that is the ratio of carbon to hydrogen. It's just not a whole number ratio. And we want it to be whole numbers because we can only have whole numbers of atoms. So to get it to be whole numbers, we're going to divide by whichever of the numbers is the smallest. In this case, 0.142. So we have 0.142 divided by 0.142, which gives us 1, and 0.284 divided by 0.142, which gives us 2. So our empirical formula is CH2. In this question, you're finding the empirical formula of hematite. As you approach this problem, you're going to trust that the values given in the problem are correct. So whatever ratio you come out with, you need to maintain that ratio. Be aware, this is going to be a little bit tricky. So the correct answer is C, Fe2O3. This sample would give you, once you do all your steps, a ratio of 1 iron to 1.5 oxygens. But we don't want to round that 1.5 all the way up to 2 because it's not really trusting the data that we got. So instead what we're going to do is multiply each of those by 2. So we can maintain that same ratio while still giving us whole number values. So we end up with Fe2O3, and the answer would not be FeO2. Our third type of calculation is finding an empirical formula based on a percent composition. We're going to approach these problems basically in the exact same way as the previous ones. We just have one extra step added on at the beginning, which is changing the percent symbol into a G for grams. So how does this work? What we're doing here is we're going to assume that we have a 100-gram sample. We're basically pretending that we have 100 grams, even if we know that we don't. Because by doing this assumption, it makes our math a lot easier. Let's say we had 100 grams of a particular compound containing oxygen, carbon, and hydrogen. And we found that the percent composition of oxygen in that compound was 51.41%. So 51.41% of 100 grams would be 51.41 grams. So if we did that same assumption for each of the elements in the compound, then our ratios should still hold true. So it doesn't actually matter what the actual masses are, as long as we know the ratio of those masses. So as you approach this problem, again, you're finding the empirical formula the same way as you've done before. You just have that one extra step at the beginning to do. So the correct answer is B, CO2. Your first step would be changing the percent symbols into G for grams. Then you take those grams and change them into moles. Then write your preliminary empirical formula and divide by the lowest number of moles and round it if necessary just a little bit in order to get the true empirical formula. Our final type of calculation in this section is finding molecular formula if we know the empirical formula. And we can, again, find that empirical formula if we know either the masses of each of the elements in grams or the percent compositions. So our first step that we're going to do as we do this type of problem is calculating an empirical formula mass. That is the mass based on the empirical formula. Then we're going to take the molar mass of the compound, which would be given to us in the problem, and divide by the empirical formula mass that you would have just calculated in step 1. And then our third step is multiplying the empirical formula, that is the subscripts in that empirical formula, by that ratio that you find in step number 2. So here's an example. We're trying to find the molecular formula of a compound which has the empirical formula of NO2. We're also told that this particular compound has a molar mass of 92.010. So our first step is finding an empirical formula mass. We're going to do it as if the molecule were just NO2. So we have 1 times the mass of nitrogen plus 2 times the mass of oxygen from the periodic table and add them up. So the empirical formula mass would be 46.005. When we compare that to the actual molar mass of the compound, we see those two numbers are different. The molar mass is much larger. So our molecule must be larger than NO2. So what we need to do in step 2 is find out how much larger it is. Our second step is finding the ratio between the molar mass and the empirical formula mass. So we'll take our molar mass on the top, that's the larger number, divide by the empirical formula mass on the bottom. That's going to be our smaller number. So we've got 92.010 divided by 46.005, and that gives us a ratio of 2. This is telling us that our molar mass, that is the mass of the molecule, is twice as big as what we'd expect based on the empirical formula. So now we're going to take that ratio and multiply each of our subscripts in our empirical formula by that number. So we had 1 nitrogen and 2 oxygens. We multiply each of those by 2. We get 2 nitrogens and 4 oxygens. So our actual molecular formula is N2O4. In this question, you're finding the molecular formula of nicotine. You're given percent composition. So remember, you're going to change the percent symbols into G for grams, change grams into moles, and then divide by the lowest number of moles to find the empirical formula of the compound. But that's not necessarily as the same as the molecular formula. So then you'll have to apply what we just learned to take that empirical formula and change to molecular formula using a molar mass of the compound. Now, the molar mass is not given to you in this problem directly. You're going to have to calculate it by taking the number of grams and the relationship between grams and moles of the nicotine. We know that for every 0.2500 moles of nicotine, that corresponds to 40.57 grams. So if we take our grams, divide by our moles, that gives us grams per mole, which is the molar mass. So you'll take that molar mass that you calculated along with the empirical formula that you will have calculated and find the molecular formula. So the correct answer is D, C10H14N2. So when we go through the steps, changing percent to grams, grams to moles, dividing by the lowest number of moles, we get an empirical formula of C5H7N, which would be A. But that is not our answer, because we need to know the molar mass of the compound to see, is that the true molecular formula? So to find that molar mass, we take our 40.57 grams, divide by our 0.2500 moles, and that's our molar mass that we can use for comparison. And what we find is our molar mass is actually twice as large as the empirical formula mass. So we have to multiply each of our subscripts by 2, and that would give us a true molecular formula of C10H14N2. So we've done percent composition which tells us the relative amount of an element in grams compared to the whole compound in grams. Sometimes, rather than telling 8% of an element within a compound, we're interested in telling the amount of a compound within a mixture. And so this is going to be measuring concentration. The most common unit of concentration in chemistry is molarity, or we could use the term 1 molar as our unit. So a solution is really just a fancy term for any homogeneous mixture. This does not necessarily have to be a solid dissolving in a liquid. We could have a liquid in a liquid, or a liquid in a gas, or a solid in a gas, and all of those could be solutions. No matter what type of solution it is, whichever substance is present in the greatest number of moles will be called the solvent. Often our solutions will be made with water as the solvent. For example, when we dissolve salt into water, the water is present in a greater number of moles, so it's the solvent. The substance present in the smaller number of moles is called the solute. So in this case, the sodium chloride is the solute. There's less of it. Together, the solvent plus the solute makes the solution. So the solution is everything together. Our definition for molarity is moles of solute divided by liters of solution. The moles of solute is essentially the part, and we're dividing by that by the liters of solution, which is the whole. So we can abbreviate molarity with a capital M, so our equation becomes capital M equals MOL divided by capital L for liters. If we want to solve for anything other than molarity, we can rearrange our equation to solve for either moles or liters. As we do this, our volume must be in liters, not microliters, not milliliters, just liters, because our definition of molarity is based on liters of solution. So one rearrangement of our equation is liters equals moles over molarity. If you're not sure about how to get that algebraic rearrangement, please double check your understanding of algebra. If you don't want to do the algebraic rearrangement yourself, you can memorize the 3 different forms of this equation. Our third form of the equation is solving for moles. So we've got moles by itself on one side of the equal sign. So our equation is moles equals molarity times liters. Again, make sure that you can do the algebra properly or just memorize it. So let's look at an example. We're trying to find the concentration of sucrose in a soda. We're given the volume of the sample in milliliters, and we're told how many moles of sugar are in that sample. So we know moles, and we have a volume, but in order to use our molarity equation, that volume must be in liters. So to change our milliliters into liters, we multiply by 10 to the minus 3 and come out with 0.355 liters as our volume of the soft drink. Now we can use our molarity equation. Molarity equals moles over liters. We plug in our moles, which is 0.133, and we plug in our liters, which is 0.355, and we come out with 0.375 molar as our molarity. Here's a second related example. We're trying to find how much sugar in moles is found in a sip of the soft drink from the previous example. Not the whole thing, but just 10 milliliters of that soft drink. And the interesting thing, because it's based on the previous example, we already know the concentration it should still be the same concentration as before, which is 0.375 molar. So again, anytime we use our molarity equation, the volume has to be in liters. So that 10 milliliter sample, we need to take our 10 milliliters and convert it into liters before we can put it into any rearrangement of our molarity equation. So we take our 10 milliliters and multiply by 10 to the minus 3, and that gives us 0.010 liters. So now we have a molarity and we have a liters, which means we can solve for moles. So we use our third rearrangement of the equation, moles equals molarity times liters. So we multiply our 0.375 molar times our 0.010 liters, and that gives us 0.00375 moles of sugar are found in that 10 milliliter sip of that particular soft drink. In our third calculational example, which is based on the previous ones, we have some sweet tea, and it has a different concentration compared to the concentration of sugar in the soda. So its concentration of sugar is 0.05 molar. We want to find what volume of the sweet tea we're allowed to drink in order to give us that same concentration of the sip of soft drink from the previous example. So in the previous example, our sip had 0.00375 moles of sugar. So we want to have that same amount of sugar, which is 0.00375 moles. So we know a molarity and we have a moles. So we can use a different rearrangement to solve for liters, our volume. So our rearrangement is liters equals moles over molarity. We plug in our moles, that's 0.00375. We plug in our molarity, which is 0.05 molar for the sweet tea. And so that tells us our volume that we're allowed to drink is 0.075 liters. Now the question is asking us what volume in milliliters has that same amount of sugar. So we change our liters into milliliters by dividing by 10 to the minus 3. And that gives us 75 milliliters. So anytime that you have grams and want to find moles, or you have moles and want to find grams, you're going to use molar mass. Going from grams to moles, you divide by the molar mass. Going from moles to grams, you multiply by the molar mass. But you don't necessarily need to memorize that fact. As long as you write out your units and set up your conversion factors properly with those units, you'll know whether something is going to go on the top or the bottom of the conversion factor, and therefore you'll know whether to multiply or divide. In this example, we're trying to find the concentration of acetic acid that we are making if we put in 25.2 grams of acetic acid into a total of 0.5 liters of vinegar solution. So our first step is going to be finding the molar mass of the acetic acid, because we need to be able to convert grams into moles in order to plug moles into our molarity equation. So we've got 4 times the mass of hydrogen plus 2 times the mass of carbon plus 2 times the mass of oxygen. And we add those up and get 60.052 grams per mole. Now that we have the molar mass of that compound, we can convert grams into moles. So we take our 25.2 grams, divide by the molar mass, which is the 60.052 that we just calculated, and that gives us 0.4196 moles as the amount of acetic acid that we're putting into our solution. Our third step is taking that number of moles and dividing by our liters to get molarity. So we have 0.4196 moles divided by 0.500 liters, and that gives us 0.839 molar as our concentration. In this question, you're trying to find the molarity of the salt water. You're given a mass in grams and you're given a volume in milliliters. In this example problem, we are trying to find how many grams of sodium chloride are needed to make 0.250 liters of a 5.30 molar solution. Again, this is using our basic molarity equation, but in slightly different ways than what you're used to. So our first step is going to be finding how many moles of sodium chloride are needed to make this solution. We know the volume and we know the molarity, so we can solve for moles using a rearrangement of our molarity equation. The rearrangement is moles equals molarity times liters. So we plug in our molarity of 5.30 molar, we plug in our liters, which is 0.250 liters, and that gives us 1.325 moles that we're going to be putting in. But we can't weigh out moles in the lab, so we need to change from moles into grams in order to figure out how much to put into our solution. Before we can do that, though, we need to know the molar mass of the sodium chloride. So that's going to be step number 2. We take 1 times the mass of sodium plus 1 times the mass of chlorine and add them together, and we get a molar mass of 58.443 grams per mole. Once we have all that information, we can use the number of moles that we're putting in and the molar mass to change those moles into grams. So we take our 1.325 moles of sodium chloride, multiply by the molar mass of 58.443 grams per mole. The units cancel out, and we end up with 77.4 grams of sodium chloride that we would be adding in to make our 0.250 liters of solution. In this problem, you're calculating how many grams of sodium hydroxide are needed to make 100 milliliters of a 1.25 molar solution. Sometimes, rather than making the solution fresh from a solid dissolving in a liquid like water, we want to do it by dilution. So dilution is taking an already made solution and adding water to it to make it more dilute. The reason why we would want to do it this way is if we can have a concentrated solution, it's going to be much cheaper and easier to store and to ship. So we can take that concentrated solution and then dilute it later to get the concentration we actually need. When we do a calculation that's based on a dilution, this is going to depend on the fact that the number of moles of the solute will remain unchanged by adding in solvent, such as water. So the moles of the solute before the dilution equals the moles of the solute after the dilution. And sometimes we abbreviate moles as N, so N would be like number of moles. So N1 moles of solute before the dilution equals N2 moles of solute after the dilution. We can also shorten our rearrangement of our molarity equation, moles equals molarity times liters. We could write this as N equals ml. And this is going to be true for a variety of different circumstances. So we could have circumstance number 1. So moles equals molarity times liters in circumstance number 1. N1 equals M1 times L1. Or this could be true in circumstance number 2. Moles number 2 equals molarity 2 times liters 2. And we know that the number of moles before the dilution equals the number of moles after the dilution. N1 equals N2. So we can set those equal to each other, and therefore we can set the other things on the other side of the equal sign equal to each other. So M1L1 equals M2L2. We could generalize this equation as C1V1 equals C2V2, where C stands for concentration and V stands for volume. So concentration times volume before the dilution equals concentration times volume after the dilution. We can do this for any variety of units of concentration and any variety of units of volume, as long as they're the same on both sides. So in this case, with our dilution equation, we can have milliliters as our volumes, as long as we're consistent about it. And that's because of simple algebraic rules. If we multiply both sides of an equation by some number or divide both sides of an equation by some number, that equation is still valid. So let's say we were dividing both sides by 1,000, going from liters to milliliters or vice versa, then the equation is still valid. So if we look at the graduated cylinders in the picture, the one on the left is our starting concentration of copper nitrate. So it's a little darker blue. And we've got a little bit smaller of a volume of it. When we add water to it, that copper nitrate gets diluted. So the color of the copper nitrate gets to be a lighter blue, and our volume is getting larger because we've added some water to it. But the number of moles of the copper nitrate is not changing between those two pictures. It's the same in both because all we've done is messed with the water. We haven't done anything to change the number of moles of the copper nitrate. So here's an example using our dilution equation. We're given a starting concentration and a starting volume. Our starting concentration is 5 molar, and our starting volume is 0.850 liters. And we're told it's diluted to a volume of 1.80 liters, so that's our new volume, V2. So we can identify our variables. C1, the initial concentration is 5 molar, V1 is 0.850 liters, and V2 is 1.80 liters. We're using our dilution equation, C1V1 equals C2V2. But in order to use this equation, we need to get the variable that we're trying to solve for by itself on one side of the equal sign. In this case, our missing variable is C2. So we need to get C2, the new concentration, by itself. To do that, we divide both sides by V2. So we get C2 equals C1 times V1 divided by V2, and then we can plug in our numbers that we identified. So the C1 and the V1 go on the top, and the V2 goes on the bottom in this case. And we come out with 2.36 molar as our concentration. With our dilutions, they should make sense. If we're starting with a concentration of 5 molar and we're diluting it, it's getting weaker. So we should get a smaller molarity for our new concentration. In fact, we do is 2.36 molar. So in this question, you're trying to find what volume of 1.59 molar potassium hydroxide is needed to make 5 liters of 0.100 molar of potassium hydroxide. So pay attention to the wording here for your 1s and your 2s. The 1s is the before set of conditions, before it's diluted, and the 2s are your new sets of conditions after it's diluted. So the correct answer is A. You have to be very careful with the wording on your dilution problems. Sometimes it will tell us the amount of liquid that's the final volume, or sometimes it will tell us how much liquid is added to the amount that's already there. So here's an example of the latter. So we have 45 milliliters of water being added to a solution that's already there. And that solution that's already there is 250 milliliters of a 0.75 molar solution. We're still using our equation C1V1 equals C2V2, but we have to be very careful about what we're putting in as that V2. Our C1 is 0.75 molar. That's our initial concentration. Our V1 is going to be the 250 milliliters that it started out as. And the V2 is going to be a total of 295 milliliters. The 250 that we started out as, plus the 45 that we added. So then we're going to solve for the molarity of the diluted solution. So that's going to be C2 that we're solving for. So our equation is C2 equals C1V1 divided by V2. And we can plug in all our variables and solve. So we come out with 0.64 molar as the molarity of the diluted solution. Sometimes we'll want to make a solution that's very dilute, that it would be impractical to do just one dilution for. Or sometimes we want to make multiple concentration CUs in our experiment so we can test those different concentrations. In each of those cases, we would want to do a serial or sequential dilution. With our serial dilutions, we're going to have a stock solution to begin with, and we will take some of it out of it and put it into a new test tube or vial or flask that has some liquid in it. So that will make our first dilution. Then that becomes our stock. So we take some out of that new vial and put it into yet another one and dilute it. Then that becomes our new stock. So we take some out of that and put it into a new one and dilute it. This is used in chemistry. It's also used in biology for plating out bacteria. So usually the bacteria solutions are too concentrated to plate directly. If you did so, the bacteria would just grow together into one big smudge and you wouldn't be able to count the colonies, which is something that microbiologists or other types of biologists do pretty frequently. So in order to get these separate colonies, the dilution has to be appropriate. So we could take 1 milliliter out of the stock, put it in with 9 milliliters of the broth that you're incubating it in, and that would create the first dilution. Then you can take 1 milliliter out of that and put it into 9 milliliters of broth. So that next vial is going to be less concentrated, and then the one after that will be less concentrated than that one. Each time it's becoming 10 times less concentrated than the one before it. So eventually you get to a test tube that's dilute enough to where you can see the individual colonies. And you may not actually know which one is going to give you the best result. So doing a serial dilution and plating all of them will give you a chance to have one that is optimal with a really good amount of colonies that you can count properly. To do our calculations for serial dilutions, we're going to have our initial stock solution, which would be our C1, and we would solve for C2, the new concentration. After that first dilution, then that C2 from the first dilution becomes the C1 in our next calculation because it becomes our new stock. So we just do this for however many new vials that we're calculating it for, and we can find the concentration of each one of them. So let's look at an example. We're trying to find the concentrations of each of these new standard solutions that we are trying to prepare. We call them standard solutions because they will be of known concentration once we make them. So we've got our stock solution and then these 4 standard solutions that we're making, which are separate from the stock solution. So we're taking 10 milliliters out of each solution, putting it into the next flask, and diluting the rest of the way to 250 milliliters. So we take 10 milliliters out of our original stock, which was 2 molar, and put it into our first flask, and then dilute to the line with water. Then we take 10 milliliters out of that flask and put it into a new one and dilute to the line with water. Take 10 milliliters out of that flask, put it in a new one, dilute to the line with water. And then finally, for our fourth one, put it in our fourth flask and dilute to the line with water. So here's how we do the calculations to find what the concentration is for each of those flasks. We're using our equation C1V1 equals C2V2, but again, we're going to rearrange it to solve for the variable that we need. In this case, the variable we need is the concentration of each new solution, C2. So the concentration in flask number 1, we're going to solve by using C2 equals C1V1 over V2, where C1 is our original stock solution of 2 molar, V1 is the initial volume that we're taking out of the stock and putting into the new flask, which is 10 milliliters, and then we divide by V2, which is the new volume that were created of the diluted solution, which is 250 milliliters. So we do 2 times 10 divided by 250, and that gives us a concentration of 8 times 10 minus 2 molar for our first Erlenmeyer flask, or rather volumetric flask. Our second volumetric flask is going to be calculated the same way, but we're not taking out of our original 2 molar stock, we're taking out of our first flask that we created. So our C1 in this case, the concentration that we're taking out of, is 8 times 10 minus 2 molar. The other variables are the same. We're doing 10 milliliters each time, and we're diluting to 250 milliliters each time. So really the only thing that's changing in this example is the concentration of our solution that we're pulling from. So when we do that calculation, we find that the molarity in flask number 2 is 3.20 times 10 minus 3 molar. For flask number 3, we're plugging in that 3.20 times 10 minus 3 molar as our C1, and we come out with 1.28 times 10 minus 4 molar as our C2. That is our concentration of flask number 3. And then flask number 4 ends up with a concentration of 5.12 times 10 minus 6 molar. We've talked about molarity, which is 1 unit of concentration. In this last section of Chapter 6, we're going to talk about some other units of concentration. We'll talk about mass percentage, volume percentage, mass volume percentage, parts per million, and parts per billion. So first, we'd like to talk about mass percentage. We've already talked about percent composition of elements within a compound, and that would be grams of the element divided by grams in the compound times 100. We can also do that same type of mass percentage, or percent composition, for parts of a mixture. We just don't typically use the term percent composition. Instead, we use the term mass percentage. Other terms that we could use are percent mass, percent weight. We could use weight percent, mass over mass percent, and each of those have little abbreviations that you could use as well. So those are all terms that we could use for part of a mixture divided by the whole mixture times 100. So our calculation we're going to use for mass percentage is mass of the component, that is the part, divided by mass of the solution, that is the whole, times 100%. So here's an example trying to find the percent by mass of glucose in spinal fluid. We're going to take the mass of the component, which is glucose, and divide by the mass of the solution, which is the spinal fluid, and then multiply by 100%. As we do this problem, the masses must be in the same unit as each other. The problem right now is that our mass of glucose is in milligrams, and the mass of the spinal fluid is in grams. So to get them to be the same unit as each other, we can either convert our milligrams of glucose into grams, or we can convert our grams of spinal fluid into milligrams. So let's say we convert our milligrams of glucose into grams. We would come out with 0.00375 grams of glucose. So then we divide by our 5 grams of our sample of spinal fluid and multiply by 100 to change from a decimal to a percentage, and that gives us 0.075% as our percent mass. In this next example, we're not calculating mass percent, We're actually using it as part of our problem. So what we're trying to find is the mass of HCl contained in 0.50 liters of a particular solution. We're told the mass percent of the solution, and we're told the density of the solution. So what we're going to do is take the volume that we're trying to solve for, our 0.500 liters, and first we're going to put it in milliliters so that we can use density, which is in grams per milliliter, as a conversion factor to change from milliliters into grams. Once we have grams, we can use mass percent, which is in grams of the part divided by the grams of the whole times 100. So when we use that, that can give us the mass of the HCl, which is what we're trying to solve for. So first of all, 0.500 liters is equal to 500 milliliters. This is opposite from a lot of the other problems we've done where we're taking milliliters and changing into liters to plug into our equations. But here, since density is in grams per milliliter, we actually need to get our volume into milliliters. Then we can take that volume in milliliters and multiply by density as a conversion factor. When we do this, we need to make sure our units are set up properly. So we want milliliters of solution on the bottom to cancel out, grams of solution is going on the top since we're trying to solve for grams, and our density is 1.19 grams being equal to 1 milliliter of solution. So the 1.19 ends up being on the top next to grams, and the 1 ends up being on the bottom next to milliliters. But you have to pay attention to those units to tell you whether the density would go on the top or the bottom of the conversion factor. So here we're multiplying by 1.19, and we come out with 5.95 grams of solution. Now that we know the mass of our solution, we can use our percent by mass as a conversion factor in a sense. So 37.2% means that out of every 100 grams of solution, 37.2 of those grams would be hydrochloric acid. So we can use that as a conversion factor between grams of our part, our component, the HCl, and grams of our whole, the solution. So since we're starting with grams of solution, we want grams of solution on the bottom of our conversion factor, and grams of our part, the HCl, is going on the top. And that relationship is 37.2 grams of HCl is going to be equivalent to 100 grams of solution. And that's just coming from that 37.2% by mass. So we do 595 times 37.2 divided by 100, and that gives us 221 grams of HCl. So in this calculation, you're finding the volume of concentrated HCl solution that contains 125 grams of HCl. You're given a density, and you're given a percent by mass. So this is similar to the previous problem, but not exactly the same. You're going to use the same concepts, but here we're trying to solve for volume of HCl solution that has that particular mass. The answer is D, 282 milliliters. You're going to rearrange the equation for mass percent in order to solve for mass of the solution. And then once you have mass of the solution, you can use the density of the solution as a conversion factor to find volume of the solution. Be careful when you're using density as the conversion factor that the units match up. Since we're starting with grams of the solution, grams will have to go on the bottom of the conversion factor, and milliliters would go on the top. So that 1.19 ends up being on the bottom of our conversion factor. So we divide by 1.19 to get our answer. So we've looked at mass percentage, so let's talk about volume percentage. It's pretty much the same concept, but with volumes. There are multiple names for volume percentage as well. We call it percent volume or volume over volume percent, and those have some abbreviation symbols as well. So for example, the V over V is telling us we have V on the top in our numerator and V on the bottom in our denominator. So both of our units are volumes. So our volume percentage is equal to volume of the solute, that is our part, our component, divided by volume of the solution, that is the whole. And again, multiplying by 100 to change from a decimal to a percentage. So here's an example of using volume percentage. We have a 70% by volume solution of rubbing alcohol. So again, that percent VOL is important to tell you that this is not a mass percentage, this is a volume percentage. And we're given the density of isopropyl alcohol, which is the main component of rubbing alcohol. And we want to find how many grams of isopropyl alcohol are in a 355 milliliter bottle of rubbing alcohol, which contains both isopropyl alcohol and some water. So our first step is taking that volume of our solution of rubbing alcohol and using our percent by volume of the rubbing alcohol to find how many milliliters of isopropyl alcohol would be in that bottle. So we take our 355 milliliters of solution. Milliliters solution has to go in the bottom of our conversion factor, and milliliters of isopropyl alcohol is going to go in the top of our conversion factor. And that 70% again tells us that 70% of the solution is our component, in this case the isopropyl alcohol. So out of every 100 milliliters, 70 of those would be the isopropyl alcohol. So we can do 355 times 70 divided by 100, and that tells us out of the 355 milliliters of solution, 248.5 of those are the isopropyl alcohol. Then we can use the density of isopropyl alcohol as a conversion factor. So we're going from milliliters of isopropyl alcohol to grams of isopropyl alcohol using the density of isopropyl alcohol. So there are 0.785 grams per 1 milliliter for our density. So we're multiplying by that 0.785, and that gives us 195 grams of isopropyl alcohol would be present in that 355 milliliter bottle. Another unit of concentration could be mass volume percentage. So this would have mass in the numerator and volume in the denominator. We can abbreviate this as M over V for mass over volume, or W over V for weight over volume. So our mass volume percentage is going to be mass of the solute, again our component, our small part, divided by volume of the solution. That's our whole thing, and then times 100%. So if we want to convert between mass percent and mass volume percent, we can use the following equation. Mass over volume percent is equal to density times mass percent, or in other words, W over W percent. So mass volume percent is not a true unit of percentage because the units are not the same on both the top and the bottom. We have mass, which would be probably in grams, and volume, which could be in milliliters or liters. So mass volume percentage is not a true percentage, but it is a quick and easy to measure in the lab or the clinical setting because masses are typically given in grams, which you would weigh out on the scale. Volumes are typically given in milliliters or liters, which you can measure in a graduated cylinder. So you can come out with the mass volume percentage by a quick division problem. So in this example, we're trying to convert from the mass percent into mass volume percent. And we're given the density of the sulfuric acid solution as 1.7323 grams per milliliter. and our mass percent is 80%. So we can just plug in our values, our 1.7323 grams per milliliter for our density, the 80% for our mass percentage, and that tells us our mass volume percentage is 138.58%. So if you think about that, that's pretty weird. Like, how do we have more than 100%? But again, it's because mass volume percent is not a true percentage. So in the chemistry lab, we don't like to use this one very much, but if you go into a medical field, you may encounter this much more frequently. Our last units of concentration are parts per million and parts per billion. We use these for really tiny concentrations. So parts per million, its equation is mass of the solute, that is the component, the small part, divided by mass of the solution, the whole thing, times 10 to the 6th. Parts per billion is mass of the solute over mass of the solution times 10 to the 9. So these equations are very similar to our mass percent equation. Our mass percent equation would be mass of the solute over mass of the solution times 10 to the 2, in other words, 100. With parts per million, we're multiplying by 1 million. With parts per billion, we're multiplying by 1 billion. So just like percent, the cent is referring to 100. 1% is 1 out of 100. 1 parts per million is the same thing as 1 out of 1 million, and 1 parts per billion is the same thing as 1 out of 1 billion. So if you had 1 billion molecules in your syringe, and one of them was the thing you were interested in, then it would be a 1 part per billion solution. So let's look at an example. The EPA has to test tap water to see how much lead is in it. And if the concentration of lead reaches 15 parts per billion, then something has to be done to treat the water to remove the lead. So we want to find that mass of the lead in micrograms that would be contained in a typical glass of water, which is 300 milliliters. We're going to also be finding what the concentration of that would be in parts per million. So we know that parts per million, we end up multiplying by 10 to the 6th in our calculation. Parts per billion, we end up multiplying by 10 to the 9th in our calculation. So they're related by a factor of 1,000. 1 parts per billion is 1,000 times smaller than 1 parts per million. So we could use a conversion, 1 parts per million equals 1,000 parts per billion. We can use the density of water to convert between grams and milliliters of water. And since that density is 1 gram per milliliter, that's a really easy conversion. So if we have 300 milliliters of water, that means we have 300 grams of water. And since most of the solution is water, we can estimate our mass of the solution to be 300 grams. So we're going to plug into our equation for parts per million. We're going to have the mass of the solute on the top, mass of solution on the bottom, and then multiply by 10 to the 6th. But we're not going to plug it in directly. We need to rearrange our equation first, since what we're trying to solve for is mass of the lead in that cup of drinking water. So when we rearrange that equation, the mass of the solute needs to be isolated by itself. So we would multiply both sides by mass of the solution and divide both sides by 10 to the 6th. So we get mass of solute, which is the lead, equals our parts per million times the mass of the solution divided by 10 to the 6th. We plug in our 0.015 parts per million, which we solved for earlier, times our 300 grams of the water, which is our mass of the solution, and divide by our 10 to the 6th. and that gives us 0.000045 grams. What we really want is micrograms though, so we're going to change it into micrograms by dividing by 10 to the minus 6, and that gives us 4.5 micrograms of lead would be in that 1 cup of tap water. In this problem, you're finding the concentration of mercury in a 50-gram sample of wastewater. The correct answer is C, 9.6 parts per million. Notice the masses are different. So just like with our percent composition problems, they need to be in the same units. So we can either get the mercury into grams or our sample into milligrams. Once we get them into the same units, then we do the part divided by the whole, multiply by 10 to the 6th, and we come out with 9.6 parts per million.